All right, so today we're going to go over aerodynamic forces, lift and drag. All right, so uh, when we're talking about lift, there is going to be a lift coefficient or coefficient of lift. This is usually determined experimentally. It does combine factors like shape and angle of attack, um, things like that. Okay, so in order to calculate it, there's two ways. There's an alternate format and then the normal format. But you need to know how much lift is being created, the area of the wing, the density of the air, the velocity. Okay. The lift of the wing usually has to be equal to the weight of the aircraft in order to for the plane to start lifting off the ground. So another way you can do it is if you know the lift, how much the aircraft weighs, that's what you'll stick in here, and then dynamic pressure and area of the wing. Okay, so in order to help apply the lift equation, you do need to convert mass into weight. So sometimes they'll give you the weight or the um, mass of the aircraft. Okay, so you'll need to take the mass, which will be in kilograms, multiply it by 9.81 meters per second squared to get you the weight, which is in this case 10,000 newtons. Okay, then you convert your velocity. Okay, so it will generally give you a velocity right here. So you will put in your new velocity here, and then the rest of this should be given. Okay, and we're looking for meters per second on that. Calculate your air density. Okay, this is all given, except for you need to know your pressure and your temperature. This should be from the atmosphere one that we went over. Um, for the calculations you'll have to do, generally they'll give you the pressure and they'll give you the temperature. Okay, so in this case it's 1.196 um, kilograms per meter cubed. So then you can calculate the coefficient of lift, assuming that the lift equals the weight of the aircraft. So if the aircraft says it weighs 10,359 newtons, then we'll take that, multiply by 2. Then you can calculate the wing area, which sometimes gives you, uh, and then your density, and then your velocity squared. And then our coefficient of lift is 1.19. Okay, so generally, a bigger coefficient of lift is better than a lower one. So, so fluid will stick to an object surface that's going through the air, which will create a boundary layer between it, and this is crucial to wing performance. Okay, airflow over the object is slower close to the object's surface. So the closer it gets to it, the slower it gets. It will remain smooth until you have a critical airflow velocity, or airflow close to the object will become turbulent. This is all represented by what's called a Reynolds number. Um, so the Reynolds number has to deal with the efficiency of the airfoil based around the laminar and turbulent flow on the airfoil. This is the only time I think we ever talk about it. So um, just in your notes, put Reynolds number has to do with the efficiency of the airfoil, and you should be good. Okay. Angle attack. So angle attack um, is the angle at which the airfoil is hitting the air. Okay. So lift increases with the angle of attack up to a stall angle. Okay. So if you have this flying at zero, you'll have less lift, but you put it in more of an angle attack, you'll be creating more lift up to a point. Okay, so then once you get up to that stall point, um, this up here becomes turbulent, so you've lost all efficiency in your airfoil. So therefore, you're not creating lift anymore, and then the aircraft will fall. Okay. Um, I'll skip this slide because we don't do anything with the Reynolds number. Okay. So I'm going to skip the Reynolds number stuff. So then drag equation, very similar to the lift equation, only now we're talking about drag. So in this case, 2 times your drag, which is usually equal to the thrust of the aircraft, area of the wing, density, velocity squared. Okay. Um, Object shape does affect coefficient of drag. You can see here, um, bullets 0.292, prisms 1.14, but an airfoil is 0.045. So to calculate drag, we'll use these formulas here, okay, to calculate the drag, which would be 436 newtons. And that's, in this case, they gave us the coefficient of drag, which is 0.05 in that problem before. So there's our 0.05, and then area of the wing, pressure, so on and so forth. So this is just the coefficient of drag formula written in a different way to help solve it. Okay, downwash wing tip vortices, pressure difference at the wing tips. You can have um, air to spill over the wingtip perpendicular to main airflow. Air flows up, both upward and rearward, forming a vortex, and then that will decrease lift on there and increase drag. So what they'll do is they'll put winglets on the tips to help get rid of these wingtip vortices, very similar to this one, and improve fuel efficiency. So that is it for that one. So the assignment for this is like so. You basically have 4 problems here that you need to answer. So it gives you the number. It's loaded 92% of its maximum takeoff weight, which will tell you what the maximum takeoff weight is right down here. So you have to convert that to newtons. Um, it gives you your standard pressure and stuff like that, so that you can find. Um, it's looking for the minimum coefficient of lift, so you can find a coefficient of lift for that. The number 2 is basically using the same stuff, but if it has a coefficient of lift, how much is available for the takeoff on the runway. So basically, you calculate this, and then it's the difference between the number you calculate and the weight of the aircraft. Then this one's pretty much kind of the same deal, and then I believe this one relates with number 3. Okay, so you go through and do your calculations on that, and then put them in a Google Doc, upload it, and we're good to go. So let me know if you have any questions.